In this week's Scholarship Chemistry tutorial session, I'm taking up question 2b from the 2017 exam. In this question, we need to identify the names of 4 mystery amino acids from this list of 20 we've been given. And as well, we need to draw the structures of E, F, and G. These compounds here are produced when a couple of these amino acids that we'll identify shortly undergo further chemical reactions to produce compounds E through G. Okay. So let's identify compound A first. We know it's not optically active. That means it doesn't have a chiral carbon anywhere in its structure. A chiral carbon is a carbon with 4 different groups attached to it. So if we look through this list right here, there's only one possibility, only one amino acid that doesn't have any chiral carbons anywhere in its structure. And that happens to be the very first one you might look at if you're going through this list from the top left to the bottom right, and that's glycine right here. Glycine has no chiral carbons in it anywhere, and that's because this carbon right here, it has 4 different things bonded to it. It actually doesn't. It has 2 hydrogens bonded to it. They're identical, so it's not a chiral carbon. This amino acid is compound A. It doesn't contain a chiral carbon. Okay, so that's easy. What about compound B? We know that compound B reacts with concentrated sulfuric acid to produce constitutional isomers compounds E and F, both of which are able to decolorize bromine water. I know that if something's able to decolorize bromine water, it's an alkene. And I know, well, concentrated sulfuric acid, it's really good at dehydrating alcohols to form alkenes. So compounds E and F are both alkenes formed in an elimination reaction when an alcohol is dehydrated. So compound B must be an amino acid with a hydroxyl group attached to it, an OH group attached to the amino acid somewhere. And there's only 2 possibilities I could find. That'd be serine, because it has the OH group right here, and threonine, which has an OH group right here. Now with serine, this is a primary alcohol, and this is a secondary alcohol on threonine. With serine, if it undergoes dehydration with concentrated sulfuric acid, I'm only going to be able to form one possible product. The double bond can only be formed right there between those 2 carbons. With threonine, however, I have a choice. I could form a double bond between these 2 carbons or down here between these 2 carbons when I dehydrate it. So I have 2 possible products I could produce with threonine, and that fits what I'm looking for because compounds E and F are both produced in this one reaction. And I know that compound F is produced in larger amounts than compound E. That tells me compound F is a major product, compound E is a minor product. And if we use Zaitsev's rule, we'll find that if we dehydrate threonine, which I've redrawn right here, if we choose to remove this hydrogen up here, we will form the major product. And that's because of Zaitsev's rule, which says the poor get poorer. In other words, the carbon in the molecule that we're considering removing a hydrogen from, if it has the fewest hydrogens compared to the other carbon down here, this one has 3 versus 1 up here, if we remove this one, we will form the major product. The poor, in terms of hydrogens, get poorer when we form the major product. So compound F is this structure right here. Compound E is this structure right here, where the double bond has formed between these 2 carbons. Okay, so we've just identified compound B, as well as the 2 products formed, one major, one minor, when it undergoes an elimination reaction. It's also a dehydration reaction when it reacts with concentrated sulfuric acid. Okay, so let's identify compound B on the sheet, and we'll move on. So threonine is compound B because it has that secondary alcohol. Serine just had a primary alcohol, so it's not capable of forming 2 different products. So threonine is compound B. Okay, what about compound C? We know that in its fully protonated form, it reacts completely with 3 mole equivalents of sodium hydroxide. That means that compound C has 3 acidic hydrogens, 3 protons that are able to be neutralized in an acid-base reaction with 3 equivalents of sodium hydroxide. So I'm looking for an amino acid with 3 protons I could neutralize with hydroxide. And right now, I'm looking around. I'm seeing something like glutamic acid. It has a carboxylic acid functional group. We know this hydrogen's acidic. It can be neutralized. So can this one down here. It has 2 carboxylic acid functional groups. But what about a third one? I don't see any structures with 3 acidic protons. But that's when I have to remember something that they said in the introduction to this question. At low pH, all the amine and carboxylic acid functional groups will be protonated. That means the amine functional groups aren't NH2 when they're fully protonated, they're NH3+. and that extra hydrogen is acidic. It's able to be neutralized. And that's exactly what we're looking for. We're looking for an amino acid that is fully protonated. They mentioned that it is fully protonated. In its fully protonated form, it reacts with 3 mole equivalents of hydroxide. So we have to remember that this is not an amine group when it's fully protonated. It's NH3+, right? So, okay, this would classify as one of the options for compound C. This could be compound C because it has 3 acidic hydrogens we can neutralize. But what other ones do? Well, aspartic acid does too. It has a hydrogen there. We can neutralize that one there too. And of course, when it's fully protonated, this will be NH3+. So of course, we can neutralize one of those hydrogens as well. And these are one of our, really the 2 only possibilities I could find. I don't think I could see any more. So we have aspartic acid versus glutamic acid in the battle to figure out which one is compound C. Okay, what other hints do we have to help us narrow it down? Well, we know that compound C reacts with 2 equivalents of methanol to form an oily product when we use a catalyst, a concentrated sulfuric acid catalyst. So, I know, what is that oily product? It sounds to me like it would be an ester. I know that esters are oily products formed when methanol reacts with the help of a catalyst with carboxylic acid functional groups, right? Carboxylic acid functional groups plus an alcohol functional group with a catalyst make esters. So, I'm trying to make an ester. And I'm told that the formula of this ester is C6H12O4N+. The big thing I'm focusing on in this formula is the 6 carbons it must have. So, glutamic acid, it has 5 C's. Aspartic acid has 1, 2, 3, 4. It has 4 carbons, 4 C's. Okay. Now, when each of these react with 2 equivalents of methanol, we're adding 2 more carbons onto this amino acid to make the ester. So when we add 2 methanols, we're adding 2 more carbons. So really it's 4 carbons plus 2. That adds up to the 6 carbons that our ionic formula must have. So this sounds like it's aspartic acid. Let's just check if glutamic acid fits the bill. Well, it already has 5 C's. When we add 2 more, when we react it with methanol, with 2 equivalents of methanol to form that ester, that product will have 7 carbons. So compound C cannot be glutamic acid because its ionic formula does not match what we're supposed to get in the question. So that means aspartic acid is compound C. Cool. One more to go. The mass spectrum of compound D has a molecular ion peak at 131. That means the mass of compound D is also 131. So we're looking for a compound, an amino acid, with a mass of 131 grams per mole. And there are 2 options right there that I see. I have leucine here, with a mass pretty close to 131, and isoleucine as well. So we have 2 options once again. We need to narrow it down. Let's see what else we are given. We are told that compound D has a C13 NMR spectrum with 6 distinct peaks. So that's 6 carbons in unique carbon environments. Let's look at leucine and isoleucine and count how many unique carbon environments they should have on a C13 NMR. So, looking at leucine, it's got 1, 2, 3, 4, 5, 6 carbons. Okay, it has 6 carbons. But these 2 carbons here, they are in identical carbon environments. So leucine should only produce 5 peaks on a C13 NMR, right? C13 NMR. It should only form 5 peaks. Okay. What about isoleucine? We've got 1, 2, 3, 4, 5. 6 carbons. We have 6 unique carbons in 6 unique environments, so this should produce 6 unique NMR peaks. So compound D is isoleucine. Compound D. There we go. So let's double check. Have we got everything? We've identified compound A to be glycine, compound B to be threonine, C is aspartic acid, D is isoleucine. We have also identified compounds E and F. And we also identified compound G. I haven't shown that off yet, but here's compound G. We know that compound G is formed when compound C reacts with 2 equivalents of methanol, and that will be the structure of compound G. Okay, I think that's everything. Thanks for watching. Hope that was helpful.